Okay, this is a recording for the Oatplex example from the textbook. This is in section 3.8, and we're going to walk through this Oatplex example. Oatplex is a breakfast cereal. Steady sales. Okay, notice steady sales. So there's no trend here. There's no trend up or down. Steady sales in the last 3 years. Table 3.1 shows the demand for the last 100 weeks. To manage and control the inventory, the manager of the store is going to forecast demand for the next 2 weeks. What do you think the demand in the next 2 weeks would be? Okay, so we have all this demand. I've got this in my Excel file on the left. Let's do this. As mentioned before, time series forecasting methods identify the pattern in past values of the time series and use it to develop forecasts for future series. Hence, the first step, as shown in figure 3.9, is to identify the type of the time series. One approach is to recognize in a graph, to graph the data. Here's the graph of this 100-week demand. It says there's not any upward or downward trend or any seasonal pattern. The demand exhibits some temporary decreases and increase for a short number of periods. Overall, it fluctuates around a certain value, shown by the L in 3.10. Hence, it is reasonable to assume the weekly demand is a stationary time series. Another reason that makes stationary time series a good fit is that, as stated, sales have been steady in the last 3 years. Oatplex seems to be in the mature phase of its life cycle. So, choosing stationary time series is the first step. Let's go to step 2. Let's choose a method. This step talks about demand as a combination of a level demand, cursive L, plus some kind of random variation or noise. Based on these ideas, there's a couple different ways that we could average or model the demand. One way is simply taking a simple average method. Let's do that. What would be our simple average method for all 100 weeks? This is our simple average. So the simple average is about 212, that's 74. Is the average of all past 100 weeks. So therefore, one method for weeks 101, 102 could be, we're going to forecast 212, that's 74. We could update week 102 with the results from week 101 if we wanted to. Another method is the moving average. You've probably seen this before in 361. The moving average takes into account a number of periods, right? There's a span. If they use the last 3 months, so let's do a moving average. N is equal to 3. What would that mean? So then we would take the last 3 months and average them this way, right? So we can go down here to the last 3 months, and we would add those up. So I could do sum of the last 3 months, 98, or excuse me, weeks, last 3 weeks. Week 98 plus week 99 plus week 100 divided by 3, and that would be 176. So let me show you my formulas here. And sure enough, that's what the book gets. So the book is at 176. We've taken the last 3. And then there's some interesting ideas here the book talks about the changing of n. Notice when n is 3, the pattern of the forecast is very different than if the n is 10. So if we take 10 weeks of data and average those, so week 11 would be our first forecast of these first 10 weeks, right? Notice the up and down movements are much less with the N, right? So there's some trade-off between how important the most recent random fluctuations are, how quickly we want to respond to the changes in demand. That's the trade-off with N. Larger N's versus smaller N's. Smaller N is we're going to be a little bit more responsive. Larger N's are we're going to be a little more smoothed out. Another approach is the weighted moving average approach. So this is saying instead of, in this case, when we had N of 3, we were looking at the last 3 weeks of demand to calculate the forecast. We were assuming in this method that each of those 3 weeks has the equal weight in the formula. But a weighted moving average says, actually, let's change the weight. So we could take the last 3 weeks again, and let's do a weighted moving average. And in this case, let's do week 1 weight of, let's follow the book here. We can just follow right along. 0.5, which means what? That means we're putting 50% of the weight on that week 1. In this case, it's the most recent week. Notice how W1 is tied to demand for the 100th week. That's the most recent week. Week 2 weight is going to be 0.4. Week 3 weight is going to be 0.1. Notice the weights always have to add up to 100. So if we did a 5-week moving average, we would need to have 5 weights, and the sum of all those would need to be 100, or 1 in this case. If we did this with the weights, and we said, okay, given this weighted moving averages, what would be our new forecast? So this is weighted moving average for 3. What we would do is we're doing the sum product. We're going to take the 0.5 times demand for week 100 plus the 0.4 times week 99, close parentheses, plus the 0.1 times the 101. And this is the 3 most recent weeks, but we're weighting them differently. And notice the difference here between the moving average of 176 and this average of 202.6, which is the same thing in the book. That's a little bit of a difference. You know, you're talking 25, you're talking more than 20% or more than 10% swing based on if you weight the most recent weeks over the 3rd week. So that can make a difference. Another method that the book talks about is this simple exponential smoothing method. And this is one where we're basically taking this concept of weights and we're weighting every single week. It turns out that there's a way to do it, and this algebraically goes through and says, okay, we're going to weight all 100 weeks, and they're each going to have a weight, W1, W2, all the way to W100. It turns out that there's an easier algebraic way to do that. If you look at all this math, it comes down to this equation right here. To find out what the forecast is for the next period, we're going to use an alpha, which is a smoothing constant. We're going to take that alpha, and we're going to assume a 0.4 alpha. We're going to multiply that by the actual demand of period T, so that first period, plus 1 minus the alpha times the forecast of that first period. And so that's how we're going to calculate the next period's forecast. So the forecast for t plus 1 is taking the alpha times the actual demand plus 1 minus the alpha. See the weights here? This 1 minus alpha plus alpha is going to be 1, right? 1 minus alpha times the forecast for that previous time period. And this is the verbal description of this equation. So the next period's forecast is equal to alpha times the current period's demand plus 1 minus alpha times the forecast made for the current period's demand. We have some more math here to look at this in detail. Let's go down and figure out what this would be. Let's follow down with the book and follow along and see what happens. What we'll do is we'll create a table kind of like this to give us our demand and forecast. And where we're going to go here is we're going to evaluate this forecast and actually try to improve it. So in an effort to build similar situation to this, similar layout to this, let me move these aside here, a few rows. And let me go ahead and insert a row at the top here, maybe 2 or 3, just to give us a little bit more room. I know we're going to need an alpha. And let me just add a little bit more space over here too. That'll give us pretty close to what the book is going for here. Putting the week in column B, the demand in column C, and then a forecast. So let's follow along here. So we have the week. In fact, I'll just go ahead and put in some language that the book uses. Demand is going to be DT, and then forecast, and we'll put a T there too, or excuse me, FT there too. Okay, let's see, we'll line this way. So what we're going to do here is we're going to create this exponential smoothing forecast given the previous demand. It's as if we were doing this week by week, okay? And then we'll find out why we're doing that here in a couple of steps. There is an assumption that what we're going to do here, this initial value is going to be 150, okay? That's the one exception to this forecast. Initial forecast is equal to the actual demand as we calculate these exponential, this simple exponential smoothing method. One of the assumptions is that the initial forecast for period 1 is equal to the demand. So right now, what else are we assuming? We're also assuming that alpha is 0.25. So I'll come up here and put my alpha 0.25. I'll put my forecast equal to 150. Let me center all this. Now we're ready for the second week to use this formula to create our forecast. So F2, talking about the second week, right? Here's how to calculate it. I'm just following along in the book. Taking my alpha, multiplying it by the demand of period 1. So here's my alpha. I'm going to go ahead and anchor that. Multiplied by my demand of period 1. See how that is D1, and that's that 150 demand, period 1, week 1, plus, and then I'm going to do 1 minus alpha. I'll anchor that again. Close parentheses times the forecast for period 1, which is the other 150, which is going to be this one. That's this equation right there. So we're going to get the 0.25 alpha times the demand of period 1 plus, open parentheses 1 minus alpha, close parentheses times the forecast for period 1. This is simple exponential smoothing forecast approach. Now when I hit enter, I get 150. And the magic here is I can double click this bottom right corner of the cell, copy it all the way down, give me a little bit of formatting on the decimals, and This column is now forecast using the simple exponential method. The alpha times the previous demand plus 1 minus the alpha times the previous forecast. Okay, and we can compare with what the book has here. We have 150, 150, 162, 25, 168, 44, 162, 58. These all look right on. If we go all the way down to the bottom, let's check our 100th week. Here's 183.05, 174.06, 198.42. Okay, so this looks like we're right on par with the book. So then the question is, okay, what is the next week's forecast? And if we were to do that, what would that be? Well, it turns out we can just copy this down because the forecast is relying on the previous week's demand and the previous week's forecast. And that is 191.54. So we got it. So there we go. We have figured out how to do a exponential smoothing using an alpha of 0.25. Now, here's where it gets really interesting. I think most of the stuff we've already done from previous course. Look where we go from here. The question is there any value of alpha that yields a better forecast than an alpha of 0.25? Why do we have to be stuck with a 0.25, right? What we're going to do now is we're going to answer that question. And the way we're going to do that is with some error evaluation. We're going to evaluate our method. Error, from a forecasting perspective, comes from subtracting the demand from the forecast. So let's build another column. This will be our error column. This will be error, and this is E of t. In fact, I could probably do a subscript here. That makes it a little bit better visually. And what's the error calculation? If I go back to the book, forecast minus demand. So we're just going to do a straight forecast minus demand all the way down. Do some formatting. And let's see how we did. Are we close? Negative 49, negative 24.7, 23.44, 7.58. These look like good numbers. 97.42, negative 35, negative 33. And notice at the bottom, we're going to total them. So that's where we're going. We are going to sum these up, and that is the bias. So if I come down here, just to follow along with the book, I'm going to take out row 101 for now. We're going to come back to that later. Let me just sum this up. What is the sum total of the error? I'm just doing a simple sum. The simple sum is negative 166.14. Okay. And then the book says, hey, what about an average? We'll come back and use that average here as well. What's the mean? So we can do an average, and the average is negative 1.66. Now, wait a minute. What's the difference here? We have a total of negative 166.14. So that's an overall across the 100 weeks. We're short, right? We're saying the demand is greater than the forecast, right, by 166 overall. The average is negative 1.66. I mean, that seems pretty good, right? So we're averaging less than 2 short. That seems pretty good. The book goes on to say, okay, but bias as the mean of the forecast errors. So it's saying bias is actually 166.14 divided by 100. This is the bias. Is actually mean of the forecast errors. Note that forecast errors are estimates of the noise. We talked about the demand plus the noise. If the demand is really stationary, and if the simple exponential smoothing method with alpha of 0.25 is a good method, then the forecast error should have a mean close to 0. So all that error should average out. The errors are fluctuating randomly above and below 0 with a mean of negative 1.6, which is close to 0. This further confirms our assumption that the Oatplex demand is a stationary demand. It's pretty valid. While bias is a good metric to evaluate, the method tends to always overestimate or underestimate the actual demand. It does not capture the accuracy of the forecast. For example, consider two forecasting methods used to forecast demand. Both have a bias very close to 0. However, the positive and negative errors in one forecast range from between negative 20 and 20, while the other range from negative 100 to 100. Which forecasting method is more accurate? Although the errors in both forecasting methods have the same mean, close to 0, the latter results in larger forecast errors and thus is less accurate, right? To aggregate the errors into one metric such that positive and negatives do not offset, we use another metric called the mean absolute deviation. This measures the changes of errors by their absolute values. So now we're going to create a absolute value metric. So let's come back up to the top. Very much like what we saw back over here. If I scroll up, absolute error. Absolute error. And that's, how do we do that? ET. Can I do the subscript too? Hey, that's not bad. Actually, kind of like it. So how do we calculate the absolute value? The absolute error? We're going to take the sum of the absolute error. So now we're just going to do, okay, what is the absolute value of the forecast minus demand? And let's sum that up. So now we have these values, and let me go back and make sure we're still aligned with the book. That's right. We're basically taking all the negatives, making them positive, and positive, keeping them positive. And we're going to sum that up. So just like we've done before, we'll come down here and we'll sum and average. And we should get 2843.40, 2843. Great. These look like they align with the book. So far, so good. What that tells us is the mean absolute deviation is 2840. Another metric used to measure the accuracy of forecasting is the mean squared error. Similar to the mean absolute deviation, we're preventing negative errors to cancel out positive errors. The difference is how individual errors impact the aggregated metrics. So while the mean absolute deviation is influenced equally by small or large errors, the MSE mean squared error is influenced much more by large forecast errors than by small errors. This is because errors in MSE are squared. Hence, MSE is an appropriate metric for situations where larger forecast errors result in significantly higher costs. Okay, this is one we'll come back to in some other problems that we'll see. MSE is an appropriate metric for situations where large forecast errors result in significantly higher cost. So let's calculate our mean squared error. This is 1330.15. If we go back up to this table, we're going to do the next one over, which is squared error. Squared error. Oops. Oh. Interesting. There we go. Squared error. And this is going to be ET squared. So we have a, let's see if I can do a superscript on this one. Superscript on the squared, subscript on the t. There we go. How do we calculate this? We're going to take the error and we're going to square it. So again, we have the forecast minus the demand squared. And let me format this, and then let me copy this down. Format the decimals. We have 2104, 612.56. I'm looking right here, 549.32, 57.43. So we're looking pretty good. And again, we're going to come down here. We're going to total and average it. And I've got a total of 133,015.31 as the total squared. When I average that out, that's 1330.15. So that's another metric that we can use, in this case specifically where large forecast errors result in significantly higher costs. Moving to the next metric, we have mean absolute percentage error. So this explains the MAD and the MSE are very useful for comparing the accuracy of two forecasts. Talks about why. But there's also the question of magnitude of the demand. If the average monthly demand for the product is about 10,000, then an MAD of 90 is very small. So this is 0.9%. Forecasting method 2 is considered a very accurate forecasting method, since on average its forecast is less than 1% above. It's talking about the 1 and 2 here. However, if the monthly demand is an average of 200, then forecasting method 2 is not an accurate measure. Its forecasts are about 45%. Hence, the key to evaluating the accuracy of the forecast is to measure its forecast errors relative to the actual value. This is where we get an absolute percentage error. So we're making this relative to the actual value. And we'll do this with this mean absolute percentage error. So we'll take the absolute error and divide by demand. And here's what that looks like. So if we come back up here, and if we go to a MAPE of 8, for example, implies that on average the forecast is off by 8%. For our Oatplex cereal, we have in figure 3.13 the absolute percentage error. This gives us a percentage. So let's do that. Let's take this one, this label, and then let's change it absolute percentage error. And that's the absolute error divided by the demand. That gives it a relative value. So we're just going to take the absolute error, which we've already calculated, and we're going to divide by that demand. And then we'll center it, give it some decimals, and copy it down. Let's see, it looks like the book has us going at 3 decimals, so I'll pull out to 3. 0.246, 0.132, 0.162. This is the absolute percentage error. So these are now relative to the demand, if that makes sense. So if we scroll back down here at the bottom of the book here, we can find the total mean absolute percentage error by, again, calculating the total and the mean. And so here we have 14.33, which helps us see that it's about 14% above or below the actual demand. That is the accuracy of this forecast. Again, assuming that the alpha is 0.25. Okay, so step 4, let's assume that the manager of the store decides to use simple exponential smoothing to forecast. This is going to significantly overestimate demand in the store. Placing large orders for the cereal ends up with large inventory. On the other hand, a forecast that significantly underestimates demand results in not ordering enough and having a large stock out. So he's trying to avoid too much inventory and a stock out. A large stock out, large inventory. Thus, the manager of the store would choose MSE that penalizes large errors as an evaluation criteria for the accuracy of the forecast method. In the previous section, we used an alpha of 0.25 to forecast demand. Choosing MSE as the evaluation criteria, the simple exponential smoothing method with an alpha of 0.25 resulted in an MSE of 1330. But is alpha.25 the best smoothing constant for forecasting weekly demand? If not, what should we use? This section teaches how to optimize the value of alpha that results in the lowest MSE. So to find the best value for the smoothing constant alpha, we need to compute the value of MSE for all possible values of alpha, and then find the value that yields the lowest MSE. This can be done using Solver. Appendix K has some information about how to use Solver. The problem we're trying to solve is the following optimization problem. We're trying to minimize our MSE by changing the alpha. And alpha has to be 0 to 1. Here's how we can set this up in our spreadsheet. Go ahead and hide a bunch of these rows here so I can try to fit more on the page. Here's what we're going to do. If you don't have Solver already showing up on your Data tab, you can go to File, Options. If you're Developer tabs, you can do Excel add-ins and get that Solver add-in to show up. And in the Data tab, the way we're going to set this up is we're going to minimize our objective cell. What's our objective cell? Our 1330.15. That is our objective. And we're going to minimize that. See that option there? We're going to minimize G107. G107 is the squared error, mean squared error. Let's see. Let me do this. Let me follow along with the book even closer by taking this row out, and that way the actual book is in complete agreement here. We're going to minimize G106. And remember to click on minimize here. We're not trying to maximize it. We're trying to minimize that error. What are we going to change? We're going to change our alpha cell, which is D2.25. Subject to the following constraints. So we need to add some constraints. One constraint is that D2 has got to be less than or equal to 1. That's our first constraint. So I clicked here, click on my D2, less than or equal to 1. I'm going to add D2 has got to be greater than or equal to 0. And I'm going to click OK. And those are the two constraints. The other constraint or the other change we need to make sure we have on our solver parameters is our solving method. We're going to use nonlinear. This is an exponential mathematical relationship. And so we can't use linear. We're going to use nonlinear, GRG nonlinear, and then we're going to click solve. And what that's going to do is it's going to run a whole bunch of numbers. And if it's set up correctly, it's going to say solver found a solution. And we'll click OK, keep solver solution, OK. Notice alpha is now 0.317. And that is the alpha that's optimized to get the lowest mean squared error. How about that? Now what we can do is we can use that as our alpha. 0.317, and we can create a forecast based on that optimized alpha. So let's do that. We have a point forecast that we're going to create, and then we also want to do a prediction interval. So let's see the point forecast. Here's that equation. We know that we're going to do 101, week 101, right? So let me just do this maybe a little bit weirdly. Is weirdly the right answer? What we're going to do is we're going to create a forecast. What is the forecast? We're going to use the smooth exponential smoothing forecast. We're going to take alpha, this is our 0.317, times the demand for week 100. Here's our demand for week 100. Plus, open parentheses 1 minus our alpha, close parentheses, times the forecast for week 100. That's it right there. And that should give us 193.2. 193.2. This is our point forecast for week 101. Now optimizing with an alpha of 0.317, which is minimizing our squared error. How about that? Now the question is, what is our prediction interval forecast? The intent here is we want to be 95% confident that the actual demand will be in that interval. A two-sided prediction interval forecast will help us find that out. A lower bound and an upper bound. Okay, this last part is finding that interval forecast. The reason why we're doing that is because we could have the same point forecast for two different forecasts, but the interval forecast gives us an idea of the level of noise in the demand. And this paragraph explains that significance. Here's the math behind what we're going to do. We're actually going to use this equation to help us find that interval forecast. So let's walk through this equation here. In fact, I might even just take this equation and copy it over to the spreadsheet here, just so we have a way to look at that. SSE is the sum of squared errors. T is the number of weeks. In this case, it's 100. So let's outline this. Let's make sure we understand what each of these are and where they are. SSE is the sum of squared errors. Where have we done that? We've actually already done the calculation. And the sum of squared errors is going to be this number right there. This is our squared error. We summed it up. That's what that number is. And let me show this here, if that's helpful. What is T? T is equal to the number of weeks. So if I were to do a max, just to give me the number of weeks here, that's going to be 100. Format these so they are aligned left. Okay, so we have two of these variables accounted for. What we're looking for is this this point interval forecast, right? This is the standard error, and we need that to be able to calculate upper and lower bound. We can use this to get our upper and lower bound. So we're into the variables here. What is our bias? We've also calculated this already as well. Our bias is going to be the negative 1.36. That is our bias. And the last thing we need is the actual answer. So let's see if we can't find our sigma of the error. And I'm going to do a little subscript here just to make sure we can see what's going on. We're trying to solve this equation now. Okay, so we have all of the variables, and we're just going to type it in. And this is going to be the squirt of, I'll do 2 parentheses. We'll do the top one first here is going to be SSE minus, it's going to be the time, 100 weeks, times the bias squared. So I'll square the bias. That's the numerator underneath the square root. And then we have a denominator of time minus 1. Close and close, 2 ending parentheses. That gets us 36.44. And let's see where we're at over here in the book. Here we are. So we've got a correct standard error computation. We put all these variables in. We get 36.44. So what does that mean? Well, the last 2 steps we need to take is we need to do a 95% prediction interval forecast. And we need to find a z-score. And we're going to do this with Excel. What we're going to find is when we use the standard normal table, we're going to find a probability distribution for that 95%. And we're going to use the 0.025. And we're going to use that to find a z-score of negative 1.96. That's going to allow us to calculate an upper and lower bound around the point forecast, right? So our standard error is 36.44. Our point forecast is 193.2. So in order to go higher than that, we want to go 193.2 plus and minus 36.44 times our z-score. And then we're going to get our upper bound, 264.62, and our lower bound, 121.77, based on a 95% prediction. So what does that mean? That means we can be 95% confident that the true demand is going to be inside these upper and lower bounds. So let's calculate that. It's probably worth it also to, maybe just for conceptual, maybe just for reference purposes, I'm going to go ahead and copy this formula into Excel as well. And this is going to be the demand for week 101. But it's going to be the interval forecast, not just the point forecast. So let's do this. We have the formula is going to be way back up to our point forecast, which is 193.24, plus we're going to take our error, 36.45. We have a little bit different rounding error from the book, right? 36.44. We're using much more precise numbers, so our rounding is going to be a little bit different. Times, and here's where we're going to use some Excel magic, should I say, to help us calculate that negative 1.96. This goes back to the 0.25. Let me see if I can describe this conceptually. If we want a 95% prediction interval, 1 minus that 95 times 100 is going to be 0.05. So we're going to divide that in half because we want the upper half. We don't want the lower half on this distribution, right? If you can visualize a distribution, normal distribution curve, we want that high 95% confidence. And the difference between full confidence and 95 is 5. We're going to divide that in half for the upper half of that. And that's going to be 0.025. We're going to use that 0.025 to calculate the z-score that's going to help us get that negative 1.96. So I'm being a little bit too fancy with this negative 1.96. I'm trying to show how to find that number using Excel. And that's going to be this norm S dist function. And that's going to give us the opportunity to say, okay, that's where we get this negative 1.926 from the 0.025, which comes from this 95% probability. So when I execute this, oh, sorry, wrong one. It's norm S inverse. My apologies. Norm S inv. We are inverting it. We're backwards engineering it. Right? We're going back into what that negative 1.96 is. So we're going to use the norm S inv with the 0.025, and that's going to get us 121.81. That gets us pretty close to the book. Again, there's some rounding errors, which we've talked about before. We're using precise numbers. The book is not rounding. I believe if we use these exact numbers, 193.2 with no other decimals, 36.44 with no other decimals, et cetera, we would get those same numbers. So this is the lower bound, and the difference between the lower bound and the upper bound is, instead of adding here, we're going to subtract. And that's where that plus or minus is right there. We're going to subtract, and that's going to give us the upper bound of 264.68, which is very close to that. Finally, the last step here in this section is, now that we know what the prediction is with 95% confidence, we can predict what week 101 will be and those intervals. We can actually do 2 weeks from now, week 102. And so let's look at this. First, since demand for Oatplex is assumed to be stationary, the point forecast for the average demand would be the same as that for week 101. In other words, forecast for 102 is 193.2. Since the forecast for week is a multi-period ahead forecast with t equals 2, we can come up with a demand. This is the equation 316. We come back up to equation 316. We're using the multi-period ahead forecast instead of the 1 period ahead forecast. This is a little bit more complicated than we'll spend. We won't spend too much time on this one this week, or in this class rather. But what we're doing is we're approaching it from a little bit different angle because we're looking at multiple periods ahead. And so there's a little bit different ways to do that. Once we do that, that gives us this 0.1005. We use that to come back into the prediction interval forecast for week 102. So let's walk through this maybe just briefly. Here's week 102. We know that because it's a stationary demand, the point forecast is going to be the same. Let me format this one. Now that we have the point forecast, the question is, how do we go from a point forecast of 193.2 to get an interval forecast for week 2? And we can do that. Notice, by the way, the bands are getting a little bit wide open. They're opening a little bit more, right? So from a 121, we're going to 118. From a 264, we're going to 268. Mostly because multi-period ahead has more uncertainty, right? The way we're going to calculate this is we need a D2. And what's our D2? We can calculate that by looking at this equation here. So that's going to be equal to 2 minus 1 times the alpha. Our alpha is 0.317, and that's going to be squared. It's going to give us a little bit different than the book. 0.1008. Again, our alpha is a little bit more than 0.317, so we get a little bit more than the 0.1005. We plug that into the equations for the distribution for 102. Excuse me, the point interval forecast for 102. But we're going to use the same, very similar formula. In fact, I could copy this in here too, if that might be helpful. We're just going to follow along with this formula here, which is we're going to take our point forecast. We're going to add it to our error. We still have the same error, 36.45, times the norm.s.in of 0.025. Then we're going to do one more times this, and it's going to be a square root. So what I'm doing here is I've got the standard error of 36.44. I've got the negative 1.96, which is our z-score, which we've used before. And then we're going to add this to it. And this is, the reason why we're doing that is because this is a multi-period ahead forecast. So that's the difference between going multiple weeks ahead versus going a single week ahead, right? Notice how this is 1 plus 0. The 1 period ahead forecast has a D1 equal to 0. So it's actually embedded in here. The 1 plus D2 is a non-zero component. We put that in here. So we're going to do the square root of 1 plus that D2, close the square root, and that should give us the 118.29, which is very close to the 118.27 as the lower boundary. And we're going to do the very similar calculation here, except instead of adding, we're going to subtract. And that will get us the upper bound of 268.19. Hopefully this has been helpful. What this means here is that this is the lower and upper bound of the point interval forecast for period in week 102. At the time of, it's a 2 week out instead of next week's forecast. Let me know if this helps. Thanks.